Hi, in this video we want to continue our discussion of how we can express the measure of an angle. So to that end we had introduced the concept of the degree, and now we'll look at the radian. We'll also discuss quadrants. We had said in the previous video that if you were to take a circle's circumference and divide it into 360 little arcs, then the angle subtended by one of those arcs would be 1 degree. So that is the definition of a degree. It's the angle subtended by an arc whose length is 1 over 360 of the entire circumference. Now this is not the only way we can express the measure of an angle. There is also the radian. So here we have a circle with a radius r. So this arc could be any number, 5 centimeters, 3 inches, whatever. Here we have an arc of the circle, and it so happens that the length of this arc is equal to this radius. So to visualize this, imagine you can take a string and just lay it along this arc. If the length of that string is equal to the length of this radius here, then this angle here is said to have a measure of 1 radian. So an angle has a value of 1 radian if the length of the arc subtending that angle is equal to the radius. As you can imagine, if we were to increase this angle so that the length of the arc is twice the radius, then the angle would be 2 radians. If the length of the arc was 1.5 times the radius, then the angle would be 1.5 radians. So in general, if you want to express the measure of an angle in radians, you simply take the length of the corresponding arc and divide it by the radius. And so here we have it. An angle defined in radians is equal to the length of the arc subtending that angle divided by the radius. Here are a few examples that should help us to get a better understanding of this. So in this case here, for example, we have that the radius is 3. Notice in all 4 cases the radius is 3 units. The length of the arc here is 2.64. So what is the angle? Quite simply, the angle is going to be equal to 2.64 divided by 3. And that will give us 0.88 radians. Now, strictly speaking, we don't have to write radian here. This is just placed here so that we understand how the angle was measured. Notice we're taking a length and dividing it by another length, and so we should end up with no unit at all. However, I do encourage you to write radian. In some books it's understood that if you see no unit, then it's radian. Otherwise, when it's degree, you put a little degree sign. So this was number 1. Let's look at number 2. In this case, the angle is going to be 7.01 divided by 3. And so now the angle is going to be 2.34 radians. If we look at number 3 here, the angle is going to be 12.39. That gives us 4.13. Never lose the intuition of what's going on here. What we're saying here is that this arc is 4.13 times longer than the radius. Always keep that in mind, that this angle is simply giving us the ratio of the length of the arc to the length of the radius. For number 4, we get that the angle is going to be 16.32 divided by 3, in which case now the angle is going to be 5.44 approximately radians. Again, remember that this means that the length of the arc is 5.44 times the length of the radius. Often it's more convenient to express an angle as a multiple of pi. So instead of saying an angle, let's say, is 5 radians, which means, remember now, this means that the arc is 5 times as big as the radius. We prefer to say it's 1.59 pi radians. Notice pi does not mean radian. Pi is simply approximately 3.14. It's just a number. But as we'll see later on, when we express an angle in terms of pi, we can more immediately visualize where the terminal side is on the Cartesian plane. So as you can see, you simply divide by pi and then express what you get in terms of pi. So for example, if I have an angle that's let's say 4.7 radians, well then that's simply going to be 4.7 divided by pi. That's 1.5, approximately 1.5 pi radians. Again, very often we don't write this term radian here. I suggest you always do. And one reason for that is that sometimes students begin to think that pi means radian. No, pi is just a number. So again, how did we get this? We said 4.7 divided by pi times pi. This gives me 1.5, so that's 1.5 pi. Notice all I've done is multiplied the 4.7 by 1, but cleverly in terms of pi divided by pi. So this is a common theme. We often multiply things by 1 in order to make them look different, but still be the same. So as you can imagine, if I give you 21.4 radians, that's simply 21.4 divided by pi radians. So what's 21.4 divided by pi? That's 6.8 roughly. So we'll see very shortly one advantage of writing it this way, and that is you can tell approximately where on the Cartesian plane the terminal side of the angle lies. Assuming that the angle is in standard position, which means that the initial side is along the positive x-axis and the vertex is at the origin. The Cartesian plane is divided into 4 areas referred to as quadrants. So this is quadrant 1, 2, 3, and 4. Note that in quadrant 1, both x and y coordinates of any point are positive. In quadrant 2, the x coordinate is negative, but the y coordinate will be positive. In quadrant 3, the coordinates x and y are negative, and in quadrant 4, the x coordinate is positive and the y coordinate is negative. A very important skill is to be able to determine in which quadrant the terminal side of an angle in standard position falls. So here's an exercise. We're given some angles and we're asked to find quadrant for each. So here's a hint. All we need to do is find out how many revolutions or how much of a revolution a certain angle represents. So if it represents more than 1 revolution, simply ignore the whole number of revolutions. So for example, if an angle represents, let's say, 2.6 revolutions, well then that's the same as 0.6 of a revolution. 5.7 of a revolution, or 5.7 revolutions I mean, then that's the same as what? 0.7 revolutions. Because every revolution brings you back to 0. So that's 1 revolution, 2 revolutions, 3 revolutions, 4 revolutions, 5 revolutions, and so on. So if an angle corresponds with less than 1/4 of a revolution, it's in the first quadrant. So that's an angle which can be reduced to somewhere between 0 and 0.25 of a revolution. If that angle happens to correspond with a rotation that's between 1/4 of a revolution and 1/2 of a revolution, that's between 1/4 and 1/2, then it's in quadrant 2. If the angle corresponds with a rotation that's between 1/2 of a revolution and 3/4 of a revolution, 0.5 and 0.75 of a revolution, then it's in quadrant 3. Remember, we're talking about revolutions, right? So here, for example, if the angle corresponds to a rotation that is between 0.75 of a revolution and 1 revolution, then it is in quadrant 4. So now we're in a position then to easily determine the quadrants of these angles. So for the first one, it's 40 degrees. So that's easy enough to see. 40 degrees places you here because that's between 0 and 90. So this is in quadrant 1. 175, well, we know that this is 180 all the way here, and up to here is only 90. So 175 puts you in quadrant 2. 250 obviously has to be somewhere between 180 and 270. So that's in quadrant 3. And 315 is between 270 and 360. So that's in quadrant 4. 456. No, that's not so easy. There are other ways to do this, but for me the easiest is to simply say 456 divided by 360. And that will simply give me the number of revolutions. That's 1.26, or 27 if I round off properly. So that's the same as 0.27 of our revolution. So 0.27 is between 0.25 and 0.5. So this is in the second quadrant. So this places us in the second quadrant, quadrant 2. Now how about this one, 1870? Well, I simply take 1870 and divide it by 360. Remember, 360 corresponds with 1 revolution, so I'm finding out how many revolutions we have. So that's 170 divided by 360. That's 5.19. So that's the same as 0.19. Notice 5 revolutions. That means 1, 2, 3, 4, 5. You go around 5 times and then you go 0.19 of a revolution. So this is somewhere between 0 and 0.25. So obviously we're in the first quadrant here. We apply the same approach here. Note there are other ways to do this, but I'm just giving you one, and if you have some other one you prefer, well, fine. So 0.6 of a radian, well, we can either express this in pi, that's the other technique I was referring to, but I prefer to just divide it by a complete revolution. So that's 0.6 divided by 2 pi. that gives me 0.095. So remember now, a complete quarter of a revolution is 0.25, so this obviously is less than 0.25. This is obviously less than a quarter of a revolution. So this is in the first quadrant. 1.9 radians divided by 2 pi radians. Notice I'm dividing it by 2 pi radians. That's 0.3. So obviously now that takes us over here between 0.25 and 0.5. So this is in the second quadrant. How about 4 radians? We'll take 4 and divide it by 2 pi. Remember 2 pi corresponds with 1 complete revolution. That's 0.64. So that's 0.64 for revolution. So that's between 0.5 and 0.75. So that's in the third quadrant. How about 5.2? Well, that's 5.2 divided by 2 pi. That's 0.8. So that's 0.82 revolutions, or 0.82 of a revolution. That's between 0.75 and 1. So that places us in the fourth quadrant. Now for 28 radians. So 28 divided by 2 pi. That gives us how many revolutions that represents. That's 4.4546 actually revolutions. So it went around once, twice, 3 times, 4 times, and then 0.46. So that's the same. When it comes to just finding where the terminal side is, that's the same as 0.46 of a revolution. That's between 0.25 and 0.5. So that's in the second quadrant. And 145, same thing. That's 23.077. So that's equivalent then for right now to 0.077. That's obviously between 0 and 0.25, so that places us in the first quadrant. One advantage of expressing angles as a multiple of pi radians is that we can easily tell the quadrant of the angle. So this is going to be 0. So an angle of 90 degrees is 0.5 pi radians. An angle of 180 degrees is pi radians. An angle of 270 degrees is 1.5 pi radians. And so we see then that if we have an angle expressed in terms of pi radians, we can easily establish the quadrant. So 0.6 radians is the same as 0.19 pi radians. To save space, I won't write radians. 1.9 radians is the same as 0.6 pi radians. 4 radians is the same as 1.27 pi radians. 5.2 radians is the same as 1.66 pi radians. 28 radians is the same as 8.9 pi radians, and 145 is the same as 46.15 pi radians. Remember, all we needed to do to make this conversion is divide by pi. So 0.19 pi obviously is going to be in the first quadrant because it's between 0 and 0.5 pi. 0.6 pi is between 0.5 pi and 1 pi, so it's going to be in the second quadrant. 1.27 pi is going to be between 1 and 1.5, so that will be in the third quadrant. 1.66 pi is between 1.5 and 2, so this will be in the fourth quadrant. 8.9 pi, 8 pi represents a complete set of revolutions. Remember, every 2 pi is 1 revolution, so this is the same as 0.9 pi, and 0.9 pi is between 0.5 and 1, so that is in the second quadrant. And 46.15, well, that's the same as a complete set of revolutions, and 0.15 is between 0 and 0.5, so that is in the first quadrant. Suppose we had an angle then expressed as 39.7 pi radians. Well, that's the same. If we take out a complete set of revolutions, that we'll be taking out the 38 pi radians, leaving us then with 1.7 pi radians. And 1.7 pi radians then would be in the fourth quadrant. So whenever we have angles expressed in terms of pi radians, it makes it easier to determine the quadrant. So this is one reason why angles are often expressed in terms of pi radians. Unfortunately, sometimes this leads students to believe that pi means radians, which is very wrong. Pi is just a number that is approximately equal to 3.14. Strictly speaking, it's the ratio of the circumference of a circle to its diameter. Okay, so that's it for this video. See you in the next one.